Go.
Wars, especially world wars, are some of the bloodiest, if not are the bloodiest wars in human history. But one thing comes from these wars, and it is technology, such as, my name is James Alongi, and for my math project, I did World War II tanks. Before looking at these two tanks, a brief history on the origin of them. During World War I, soldiers fought in trenches, and in between these two trenches was an area called No Man's Land. Soldiers would have to charge across No Man's Land, and they would usually get shot down by machine guns, thus creating a need for a new technology, which was the tank. The British pioneered tank technology with their British Mark I tank, and by today's standards, it wouldn't be very advanced. It could barely move over 5 miles per hour. It would move even slower than that because of the swampy terrain. Before looking at these two tanks, a brief history. Before looking at these two tanks, I need to explain the mechanics of tank combat. Penetration is when a tank shell goes through another tank's armor, and the amount of penetration that a tank shell has is calculated with this equation, where B is the amount of penetration in millimeters, V is the velocity of the shell in meters per second, P is the mass of the shell in kilograms, K is the resistance constant, which will always be 2,400 because all World War II tanks are made out of steel, and that's a number for steel. And D is the caliber of the shell in millimeters. There are different types of shells that tanks shoot, such as kinetic energy penetrators, or armor piercing, which the mechanics are shown in this diagram here, where when the armor piercing shell hits the tank's armor, it cracks it and it uses the kinetic energy to push its way through and hits the nail. Another type of shell is high explosive anti-tank ammunition, and this works very differently from armor piercing. When high explosive anti-tank ammunition hits a tank, it creates a small concentrated explosion on the armor that creates a hole in it, and it goes through that hole. Another shell is high explosive, and most tanks carry this shell, but didn't use it against other tanks because it has no anti-tank purposes, and they would load it for shooting at infantry and firing at a wall or trying to take down a building, etc. Another thing with tanks is the armor. If you look at these two tanks, they have sloping on their tanks. Why is this? Because that increases the thickness of their armor. This diagram shows this line as the actual thickness of the armor, this line as the effective thickness of the armor, and creating a right triangle with those two lines, with the effective thickness being the hypotenuse of the right triangle. By definition, the hypotenuse has to be longer than the two legs. Because it's a right triangle, basic trigonometry can be used to yield this equation to figure out how long the effective armor will be. There are also different ways that the armor is created, such as rolled homogeneous steel armor, which is when a single steel plate is put through a roller and can be bent by a very small margin. These plates will be welded together, as shown on the front of this tank. Another type of armor would be cast homogeneous steel armor, where, as the name states, the cast will be made and molten steel will be poured into the cast, cooled, and it can make the irregular shapes that rolled homogeneous steel could, such as the side of this turret or the front and side of this tank turret. Another type of armor is spaced armor. This was when thin steel plates were placed away from the hull of the tank, and these were there to combat high explosive anti-tank ammunition. Because when these shells hit the thin steel plates, it would cause them to detonate prematurely and have no effect on the actual tank. Now, as you understand the mechanics of tank combat, you could apply these to real-life tanks, such as the T-34. T-34 is a Soviet medium tank, and the fact about it is, it's the most produced tank during World War II. It's equipped with a 76.2 millimeter F-30 anti-tank. Putting its numbers into the penetration equation of 680 meters per second shell velocity, 6.3 kilograms shell mass, 2,400 steel resistance constant, 76.2 millimeter shell caliber, can be concluded that the T-34 has 81.5 millimeters of penetration. If you look at the front of the T-34, it's angled at 30 degrees, and its actual thickness is about 45 millimeters, which, put into the equation, yields 90 millimeters of effective armor. On the other side, we have the Panzerkampfwagen 4, or the Panzer IV, and it is a German medium tank and the main tank used by Germany during World War II. It's equipped with a 75 millimeter L-43 anti-tank gun, and putting its numbers into the penetration equation of 790 meters per second shell velocity, 6.8 kilogram shell mass, 2,400 steel resistance constant, 75 millimeter shell caliber, it can be concluded that Panzer IV has 99.1 millimeters of penetration. If you look at the front of the Panzer IV, it doesn't have any sloping. Therefore, its actual thickness of 50 millimeters is its effective thickness, which is 50 millimeters. Looking at both tanks, the question is, which tank is better? Just looking at the numbers, it's impossible to tell which tank's better because factors such as infantry, terrain conditions, weather conditions, and skill of the crew can all affect how well these tanks did in battle. Just looking at the numbers and statistics, it's impossible to tell which one is more efficient and better. All in all, in the end, tank combat is more advanced than just shooting the bigger gun at the other tank and homing goes through. Factors such as what shell you're firing or how thick your armor is can all affect the outcome of the battle. Modern tanks have more advanced technologies and more advanced calculations. Any questions?